Now we turn to Mars. As we've said already, Mars is a transitional world, somewhere on the boundary between the geologically active worlds like Earth and Venus, and the geologically dead worlds like the Moon and Mercury. More clearly than any other world, Mars shows what it's like when a planet used to be geologically active but has slowed down since. Our understanding of Mars has also shifted over the last few decades, which is part of why we call this section the changing faces of Mars. You may have seen the picture at the bottom showing a grainy, low-resolution image of a hill in the region called Cydonia. It looks a bit like a face, doesn't it? This picture generated a lot of popular speculation after it was taken back in the mid-1970s by the Viking spacecraft. However, when we see a more modern, higher-resolution image of the same feature, we start to understand how much of our earlier picture of Mars has had to be replaced as we've gotten a clearer sense of what Mars is really like.
If you missed the old face on Mars, don't worry. Here's what many scientists like to call the real face on Mars, Gala crater. It seems much happier than the old one anyways. We're going to start by looking at some basic Mars statistics and seeing how it compares with some of the other terrestrial planets. Then we'll run through the major types of geological processes on Mars. We'll talk about impact cratering and see what the planet's cratering history tells us. Then we'll look at volcanism and tectonics and how these have shaped parts of the planet's surface. Finally, we'll discuss erosion and see how erosion has evolved on Mars over time. We've already seen that Mars is a terrestrial planet. This means that it's a small planet made mostly of rock and metal. Unlike the Earth, there are no clouds, no oceans, and no vegetation covering the surface, so we can see the rocky crust clearly, even from orbit. Mars is 50% further from the Sun than the Earth. This means that any given spot on Mars is getting around half as much sunlight as the Earth is, so the surface temperature is quite a bit colder than the Earth. The planet is also only 1/10 the Earth's mass. You should already know what this implies. The small mass of Mars means that gravity is much weaker here. It's about 1/3 as strong as on Earth. For geology, this means that large features like mountains can stick up higher because there's less gravity pulling them down into the crust. Finally, Mars has a much thinner atmosphere than the Earth. The air pressure at the surface is less than 1% of what we experience at sea level. You would have to go up 50 kilometers in our atmosphere to get an air pressure this low. So in the words of the Big Bang Band, Mars is rusty and dusty and cold, so cover your head.
As we know, impact cratering is the key to showing us the amount of geologic activity on the surface of a world. Here's a map of the surface of Mars, with the largest obvious impact craters shown as white circles. A few of the large impact basins are also named on the map. One of the first things scientists noticed when they started making maps like this is that impact craters are not spread evenly around the planet. Most of the impact craters are in the southern and eastern parts of the planet. You can draw a wavy line across the planet that divides the region with most craters from the region with virtually none. When we add a map of Martian topography onto this, we see how the number of craters is tied to elevation of the surface. All of the craters are in the higher elevation areas known as the southern highlands. On the other hand, the northern lowlands, the large low plain that covers most of the northern hemisphere, is virtually crater-free. There is one obvious exception to this. The highest elevation section of Mars is the Tarsus Bulge, a huge plateau with large volcanoes on it in the western hemisphere near the equator. This bulge includes the highest elevations on Mars, but there are virtually no large craters on it. Also notice that the lowest elevation on Mars is in the south, the Hellas Basin. In fact, This is a single huge impact crater, like the impact basins that formed the mare on the Earth's moon.
More recently, scientists have been able to refine their picture of the Martian cratering history. By using ground-penetrating radar, they have been able to find round impact craters under the visible surface. What they've found is shown here. There are a lot more round features that look like impact craters in the northern hemisphere. In fact, there are as many craters in the north as anywhere in the south. But in the north, these are buried under a layer of less dense material, probably some sort of sediment. So they show up on a radar map, but not a visible light image. Note that the irregularly shaped strips in the north are artifacts of how the satellite generated the data, not real features in the crust. There are also some buried craters in the south, though not as many. However, the Tarsus bulge in the west still has fewer craters than most other parts of the Martian surface. Most of the large craters here really have disappeared from the crust completely.
The most heavily cratered parts of the southern highlands have almost as many craters as the highlands areas of the moon. This suggests that this area may be approaching 4 billion years old. In fact, the first spacecraft that flew past Mars in the mid-1960s took their close-up pictures of these old cratered highlands. When scientists got these first pictures of the surface, they thought they were seeing a world that was a lot like the Earth's moon, and were afraid it would turn out to be just as crater-dominated. It wasn't until the Mariner 9 spacecraft went into orbit around Mars in 1970 and started mapping the whole planet that it became apparent that Mars has a much more complex history than the moon. This picture shows a more modern spacecraft image of the southern highlands. That large bright area isn't the South Polar Cap. It's a bank of cloud in the deep Hellas impact basin. The basin is deep enough that the air is thicker here than anywhere else on Mars, and there's just enough moisture in the air that you can get morning ground fog in the floor of the crater.
Even in some of the earliest pictures of Mars, some of the craters seemed different from craters seen on the moon. Instead of the usual ejecta blankets around the crater, there were rounded lobes of material that appeared to flow out away from the impact site. These are known as rampart craters, and they appear to be telling us about the history of the Martian soil. On the moon, the ground is bone dry, drier than the driest deserts on Earth. But at some places on Mars, the soil has been rich with ice like the permafrost in the Arctic regions on the Earth. When impactors hit this soil, the ice melted and the soil flowed as mud all around the craters. Rampart craters are most common near the poles, especially the South Pole, where we have other evidence that there is ice near the surface. Closer to the equator, only fairly large craters show this feature, suggesting that if there is ice, it's much deeper in the soil.